So the next application is that we have to find out electric field intensity due to a given charge plate, and we are assuming that this charge plate is having infinite dimensions. So this is a given sheet. Suppose, for example, I am having this sheet. So suppose on one side of this there is some positive charge which is uniformly distributed and its surface charge density is sigma. So there is a point near about this sheet where we have to find out electric field intensity. So like this is the sheet. So if I look at this sheet from a side, this sheet will look like this. It looks like a straight line. It is not a straight wire. It is a plain sheet, but it is kept perpendicular to the plane of the board. So by this picture it will be easy for us to derive the electric field intensity. Okay, so let us start the derivation. The first thing which we have to do is we have to assume the Gaussian surface, as all of you know. So if you think about the Gaussian surface in this case, undoubtedly it is going to be a cylinder. So suppose there is a point P which is at a distance r from the charged sheet where I have to find out electric field. So what I am going to do, the Gaussian surface I am going to take is cylindrical surface. So half of the cylinder will be on this side and half of the cylinder will be on this side. It's like, suppose this is the sheet. So I will be having half of the cylinder on this side and half of the cylinder on this side, like I have shown in this diagram. Okay. So let us take one more point at the same distance on other side as well. So this will be the Gaussian surface, which is a cylinder. So the total length of the cylinder will be 2r, and suppose area of its base is A only. So this is about the Gaussian surface which we have taken a cylinder. Okay, now the next step, that is to find out the flux by definition. So as in case of straight wire, the Gaussian surface was cylindrical surface. So for finding out the flux, we had to break this term in three terms due to three different types of surfaces. So suppose this is surface 1, this is surface 2, this is surface 3. Surface number 1, electric field will be away from the positive charge and area vector for this surface normally outward. So they are in same direction, that is why theta in this case will be 0. I hope it is clear to you, because it is positively charged, so electric field has to away from it. So this is the direction of electric field, and for this face of the cylinder, area vector has to be normally outward, so that is also directed in the same direction, that of electric field. That is why theta will be 0. Now this is the curved surface. So at this point, electric field due to this sheet, it will be away from it, but area vector will be normally outward. So in this case, it is clear that theta is going to be 90 degree. Now for this face, again electric field is away from the charged sheet and area vector will be normally outward. So even for third surface, theta is going to be 0 degree. Now, so this term which will be written as for three different surfaces, I am not writing down the term. Now for surface number 2, theta is 90 degree, so this term will become 0, and for surface 1 and 3, theta is 0, so cos 0 will be 1, so the integral will be simply integral EDS plus integral EDS. There won't be any circle now. So one term will be there for the surface number 1 and one term for surface number 3. So here comes the role of symmetric surface. Because surface is symmetric, that means its distance. So because surface 1 and surface 3, they are symmetric with respect to the charge sheet, so that means electric field at this surface, that will be equal, and as well as for this whole surface and for this whole surface, electric field will be constant as well. So these electric fields, they can be taken out of the integral. So we have E integral ds for surface 1, E integral ds for surface 3. So integral ds means sum of the area elements, which will give us this whole area, which we have already assumed to be A. In the same way, this area will be A. So this term will become E into A. This will also become E into A. So this term becomes 2EA. So this is the flux by definition, and this is equation number 1. Now next step is to find out the same flux using Gauss law. Using Gauss law, this flux can be written as 1 upon epsilon naught times of net charge. Okay. To find out the net charge, let us identify that how much area, how much part of this sheet it is lying inside the Gaussian surface. So since this much area is A, so this area of the sheet which is inside the Gaussian surface, it is also going to be A only. So if A area is inside, surface charge density is sigma. Surface charge density sigma means unit area of the sheet will be having a charge equal to sigma. So 2 units will be having 2 sigma, A units will be having A sigma. Using this, we can have that flux is 1 upon epsilon naught times of sigma A. This is equation number 2. Now the last step, we have to compare both of these equations. So comparing equation 1 and equation 2, we have that twice of EA is equals to sigma A upon epsilon naught. A and A will cancel out, and from here we have E equals to sigma upon 2 epsilon naught. So this is the final result of electric field intensity due to the charged sheet. And this point is very important, that as you can see, electric field, it is not depending upon R, where R was the distance from the sheet. So that means if we increase or decrease the distance of the point from the sheet, electric field is going to be same. So that means electric field is independent of R. So this is the only case in which electric field remains independent of the distance.